Have you ever gazed at the night sky and wondered, where did it all come from? What sparked the birth of the universe as we know it? It's a question as old as humanity itself, the curiosity about our cosmic origins that has sparked countless myths, religions, and scientific theories. The universe, in its vastness and complexity, has been the subject of fascination and scrutiny for centuries. It's a realm where time and space intertwine, where energy in its various forms dances around, creating celestial bodies like stars, planets, and galaxies. It's a place governed by laws, both classical mechanics and relativity, that dictate the behavior of matter and energy. But let's take a step back and ponder over its origins. Where did it all start? The most widely accepted scientific explanation is the Big Bang theory. According to this theory, the universe began as an incredibly hot, dense point nearly 13.8 billion years ago. Yes, the universe was once crammed into a spot so infinitesimally compact that it was essentially a dimensionless point. Then, in a fraction of a second, it expanded in an event that laid the groundwork for the universe as we know it today. The universe didn't just expand though. It also cooled down, allowing the formation of subatomic particles and simple atoms. These atoms clumped together over billions of years, forming stars, galaxies, and everything else we see today. From the tiniest speck of dust to the largest galaxy, everything in the universe is a product of this cosmic evolution. Yet the universe is much more than just what we can see. There's a lot more matter out there than stars, galaxies, nebulas, and interstellar gas. There's also dark matter, an elusive and unseen form of matter that we know exists because of its gravitational effects on visible matter. And let's not forget dark energy, a mysterious force driving the accelerated expansion of the universe. So, let's delve into the realm of cosmology and attempt to unravel the mysteries of our universe's origins. After all, our quest for understanding is as vast and enduring as the universe itself. The Big Bang theory, a term coined by astronomer Fred Hoyle, is the leading explanation about how the universe began. Picture this. Initially, all the energy and matter of the universe were concentrated into a point of almost infinite density and heat, something we refer to as the initial singularity. Then, in a moment less than the blink of an eye, this singularity began expanding. This expansion wasn't like a balloon inflating, but more like the rapid and accelerated stretching of the fabric of space itself. This period, known as the inflationary epoch, occurred at around 10 to the negative 32nd seconds after the Big Bang. As the universe expanded, it also cooled down. This cooling allowed the four known fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, to separate from each other. The universe continued to cool and expand, and eventually, the first subatomic particles began to form. These particles were the building blocks of matter. Over time, they combined to form simple atoms, mostly hydrogen and helium. These atoms were scattered across the universe, floating freely in space. But gravity, always at work, began to draw these atoms together. The most dense regions of the universe attracted more and more matter. Over time, these regions of concentrated matter began to form the first structures in the universe. And so, the first stars and galaxies were born. But this is not where the story ends. The universe continued to evolve, shaping and reshaping itself into the complex cosmos we see today. From galaxies and stars to planets and moons, all of existence traces its roots back to that initial singularity and the Big Bang. So there you have it, the Big Bang theory. It's a tale of expansion, cooling, and the formation of everything we see around us. From a point of almost infinite density and heat, the universe expanded and cooled, birthing the cosmos we see today. But the universe didn't stop growing after the Big Bang. In fact, it's still expanding today. This expansion began with a phase we call the inflationary epoch, a blink of an eye after the Big Bang, when the universe expanded faster than the speed of light. All the energy and matter that were initially present became less and less dense as the universe continued to grow. In these early moments, the four known fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were inseparable. But as the universe cooled, they began to act independently, shaping the cosmos as we know it. This cooling process was crucial. It allowed the first subatomic particles to form, which later combined to create simple atoms. The universe was now a vast, expanding soup of particles. but it was far from the structured cosmos we know today. The next significant phase in the universe's expansion was the formation of giant clouds of hydrogen and helium. These clouds were gradually drawn to the places where matter was most dense, creating a cosmic tug-of-war between matter and energy. This process eventually led to the formation of the first galaxies, stars, and everything else we see in the universe today. What's fascinating is that the universe didn't just expand in size, it also changed in structure. Over time, matter gathered into a foam-like structure of filaments and voids, allowing other forms of matter to come together into visible structures. This unseen matter, known as dark matter, exists alongside the rest of the physical universe and plays a crucial role in shaping it. So, while it may seem like the universe's expansion is a simple process of getting bigger, it's much more than that. It's a story of transformation, from a hot, dense point of energy to the vast structured cosmos we see today. As the universe expanded and cooled, it set the stage for the formation of complex structures. This process continues even now, billions of years later, shaping the cosmos and our place within it. In the vast expanse of the universe, matter began to clump together, forming the first stars and galaxies. Picture a cosmic ballet where particles pirouette in the grand theater of the cosmos, gradually coalescing into majestic structures. This elegant dance began with the simplest of elements, hydrogen and helium. In the early universe, these light elements were scattered across space like an immense ethereal cloud. But as time passed, gravity, the great choreographer of the universe, started to work its magic. It gently tugged at these clouds, guiding them towards areas where matter was most dense. This gravitational pull was like a cosmic call to arms, beckoning the hydrogen and helium to convene in these dense regions. As these clouds drew closer together, something extraordinary started to happen. The pressure in the heart of these dense pockets of gas increased, and with it, the temperature soared. This intense heat and pressure caused the hydrogen atoms to collide and fuse together, a process known as nuclear fusion, giving birth to the very first stars. These stars were not solitary dancers in the cosmic ballet, however. They gathered, forming clusters that we now know as galaxies. Each galaxy, a swirling ensemble of billions of stars, each star a glowing testament to the power of gravity and nuclear fusion. But these early galaxies were not the grand spirals we're familiar with today. They were smaller, irregular, and chaotic. As they collided and merged, they grew, evolving into the diverse array of galaxies that pepper the cosmic landscape today. These early stars and galaxies were the building blocks of the universe as we know it. They were the first steps in a cosmic journey that has led to a universe teeming with a multitude of celestial bodies, each with its own story. Each a vital part of the cosmic ballet that began over 13 billion years ago. Yet the visible universe, stars, galaxies, and gas clouds is just the tip of the cosmic iceberg. As we delve deeper into the cosmos, we encounter mysteries that challenge our understanding of the universe. Among these enigmas are dark matter and dark energy. They're called dark, not because they're devoid of light, but because we have strong indirect evidence of their existence. Yet we haven't directly detected them. Imagine the universe as a theater, where stars, galaxies, and gas clouds are the actors we see on stage. But behind the scenes, dark matter and dark energy are the unseen stagehands, controlling the behavior of these celestial players. Let's begin with dark matter. It's a form of matter that doesn't interact with light or other forms of electromagnetic radiation, making it invisible to our current detection methods. Despite its invisibility, we know dark matter exists because of its gravitational effects on visible matter. It's like an invisible puppeteer pulling the strings of galaxies and stars. Dark matter came into existence alongside the rest of the physical universe, gradually gathering into a foam-like structure of filaments and voids, which allowed other forms of matter to cluster into the visible structures we see today. And then there's dark energy, an even more elusive concept. Dark energy is thought to make up nearly 70% of the universe's energy and mass. It's the mysterious force that's accelerating the expansion of the universe, like an unseen director guiding the cosmic drama. Together, dark matter and dark energy make up around 95% of the universe. They're the invisible majority, silently shaping the cosmos. So the next time you gaze up at the night sky, remember that the stars, galaxies, and gas clouds you see are merely the visible tip of an enormous cosmic iceberg. Beneath the surface, dark matter and dark energy are at play, conducting the symphony of the universe. These unseen forces shape the universe in ways we are just beginning to understand. Our understanding of the universe's origins also informs our speculations about its future, and possibly its past. The universe, as we know it, began with the Big Bang. But what was before this cataclysmic event? Some scientists propose that our universe is not the first, but one in a cycle of many, each birthed from the remnants of its predecessor in an endless loop of Big Bangs and Big Crunches. Another mind-bending idea is that our universe is just one of many, existing in a vast multiverse. Each of these universes could have its own laws of physics, its own history, and possibly its own form of life. This concept of a multiverse challenges our understanding of space and time, suggesting that our universe is but a tiny bubble in an infinite cosmic foam. Turning our gaze forward, what does the future hold for our universe? There are several theories. One is the Big Crunch, where gravity eventually halts the universe's expansion, causing it to collapse back into a singularity, possibly sparking another Big Bang. Alternatively, there's the Big Freeze or heat death scenario. As the universe continues to expand, stars will burn out, galaxies will drift apart, and all matter will gradually decay into radiation. The universe in this scenario would become a dark, cold, and desolate place. There's also the Big Rip theory. If dark energy, the mysterious force that's accelerating the universe's expansion, continues to grow stronger, it could tear galaxies, stars, and even atoms apart, leading to a universe filled with isolated particles. These theories might seem grim, but they're billions, if not trillions, of years in the future. And who knows? Perhaps by then, we'll have found new homes in other universes. Whether we're living in one of many universes, and whether the universe will end in a Big Crunch or a Big Freeze remains to be seen. But what exactly do we mean when we talk about the universe? The term universe is a broad one that encompasses all the known and unknown, seen and unseen, tangible and intangible aspects of existence. The physical universe, for starters, is all of space and time, often collectively referred to as space-time, and everything that lies within it. This includes all forms of energy, from the visible light we see to the invisible electromagnetic radiation, and all matter, which comprises everything from the tiny particles that make up atoms to the vast galaxies that populate the cosmos. But the universe is not just a collection of objects floating in space. It's a complex, interconnected system governed by physical laws that determine how energy and matter behave. These laws, such as the laws of conservation, classical mechanics, and relativity, are as much a part of the universe as the stars and galaxies they govern. When we speak of the universe, we're also talking about the contents of intergalactic space and the planets, moons, and stars that are scattered across it. These celestial bodies, together with the interstellar gas that permeates the cosmos, make up a significant portion of the universe's physical contents. Yet the universe isn't limited to the physical. Some philosophers and scientists argue that abstract concepts such as mathematics and logic should also be included in the definition of the universe. These are, after all, the tools we use to understand and navigate the cosmos, to predict the behavior of energy and matter, and to probe the mysteries of existence. So when we talk about the universe, we're talking about everything that exists, everything that has existed, and everything that will exist. We're talking about a vast cosmic expanse that's teeming with energy and matter, governed by physical laws and perhaps even shaped by abstract concepts. The universe is everything that exists, has existed, or will exist. A vast cosmic expanse that continues to captivate our curiosity.